Okay, let's talk a little bit about polarity. Polarity, you can have covalent bonds where the electrons are shared, and if they're equally shared, they're nonpolar covalent bonds. So they're equal or almost equal electronegativities. Diatomic elements like H2 or N2 are perfectly nonpolar, but if it's close but non-zero, we'll still call those nonpolar covalent bonds. If they're not equal sharing, you're going to have polar covalent bonds. And so that means the electrons in the bond lie much closer to the more electronegative element. If we look at HF, fluorine has got an electronegativity of 4, hydrogen 2.1. The difference is 1.9. That is a very polar bond, even though it's still considered covalent. If we compare that to HI, there's only about a 0.4 difference in electronegativity. Still polar, but only slightly, almost enough to ignore, as we'll find. Generally speaking, if the electronegativity difference is 0.4 or less, we generally say that bond is essentially nonpolar. The reason is carbon has an electronegativity of 2.5, hydrogen at 2.1, and in organic chemistry, that carbon-hydrogen bond is considered nonpolar. If it's greater than 0.4 but less than 1.5, we're generally going to say that bond is polar but covalent. There's a significant amount of polarity now, so the bond is polar. Between 1.5 and 2, that is sort of a gray area. Usually if it's two nonmetals, we'll say it's covalent. If it's a metal and a nonmetal, then we say it is ionic. Greater than 2 is generally going to be a metal-nonmetal combination, and that's going to represent an ionic bond. Molecules where you have polar bonds, if you've got an asymmetric distribution of the charge that's generated by that, then you have what's called a dipole moment, and your molecule is polar. For example, if we look at our HF and HI again, HF is pretty doggone polar. HI, while the bond is somewhat polar, we're going, not so much. Sometimes you do get nonpolar molecules with polar bonds. There are two conditions that must be true for it to be polar. There has to be at least one polar bond or one non-bonding pair of electrons, something to make the geometry not symmetric. And those bonds or non-bonding pairs have to be arranged such that they don't cancel with one another. For example, this linear molecule, the polarities would cancel, so it's nonpolar, but a bent molecule would in fact be polar. Here are some examples of that. Our friend CO2 has polar bonds, negatives on the end, positive in the middle, but hey, there's no poles. Opposite ends of the molecule have to have opposite charges. For the water, this end of the molecule, the oxygen end of the molecule, is negative. The hydrogen end is positive. Now I've got ends of the molecule that have opposite charges, so now it's polar. It has poles. Now, HCl is polar. Because if you got a polar bond and it's diatomic, you've really got no choice. In the case of the carbon tetrachloride, you've got polar bonds, but they're all equal and oppositely spaced, such that you're not really going to get a net poles on the molecule, so that's nonpolar. Now, nitrogen has a non-bonding pair of electrons up here, so now the nitrogen end can be negative, the hydrogen end can be positive. I've got poles. Boron trifluoride, even though those are pretty polar bonds, it's all equal and opposite, so nonpolar. Another way you can get polarity is asymmetric substitution. That is, one of the atoms attached to the central atom is different. Here we have a chloromethane. So this hydrogen end of the molecule can be positive, the chlorine end can be negative. So I, in fact, do get poles. All these geometries do form shapes based on the hybridization, overlap of, in our case, sp and d orbitals. And they have the same shapes as the VSEPR theory. And we kind of ran through this on the chart, but two regions of high density is linear, hybridization sp, so that's 1s and 1p kind of mixed together. 3 is trigonal planar, so it's sp2, so it's 1s and 2p's. 4 is tetrahedral, so 1s and 3p's, sp3. To get the 5 and the 6 to violate the octet rule, there has to be some other orbitals those electrons can go into, and those are your d orbitals. So trigonal bipyramidal is sp3d. So it's mixing in a d orbital to accommodate the extra electrons. 6 is octahedral, and it's got to mix in 2 d orbitals to be able to hold all the electrons, so sp3d2. So sigma and pi bonds. Sigma bond is a head-to-head overlap of the orbitals, where a pi bond is a side-to-side overlap of the p orbitals in our case. And so what often happens is that a single bond just represents sigma. A double bond is a sigma and a pi. A triple bond is a sigma and 2 pi bonds. And so once you get the Lewis structure, all you really have to do is count and you can get those. So we're going to work through a couple of structures and we'll do everything. We'll get the Lewis structure, we'll do the geometries, the angles, the polar, nonpolar, and the hybridization. And we'll do it for these that we worked on that were violating the octet rule. Okay, these are some of our violations to the octet rule. BEH2, we want to get the geometries and stuff now. So we got 2 bonds, 0 non-bonding pairs. And so that gives us a linear geometry for electronic and molecular. And that would give us an sp hybrid with 180-degree bond angles. Even if these bonds were polar, they're symmetrically arranged, and so this is a nonpolar molecule. If we move on to this one, we got 3 bonds, 0 non-bonding pairs. So that's going to be trigonal planar. So that means it's going to be sp2 hybrid with 120-degree bond angles. And this is all, again, equal and opposite, so it'll be non-polar. SF6, I got 6 bonds, no non-bonding pairs. So that's going to be octahedral. And that's going to be sp3d2. And you're going to have mostly 90-degree bond angles. If you really want to go top to bottom, even though you're not going to get straight there without going through the plane, that would be 180. And this molecule is nonpolar. Last but certainly not least, I got XEF4. So I got 4 bonds, 2 non-bonding pairs. So this still adds up to 6, so it's octahedral, but square planar. And so again, that's going to be sp3d2 because of the octahedral. There's 90-degree bond angles, and across the plane there are 180. And this molecule is nonpolar as well. Okay, now here's just a couple of commonly encountered molecules, and I've drawn them. Let's go through the same thing we did on the previous problem. But notice I've drawn these a little differently than I drew them earlier in the notes, because I'm drawing them to represent their geometries now. Sometimes you won't be able to get that until you figure out what the Lewis structure is, and you might have to redraw it to get the geometry. In this case, I got 2 bonds and 2 non-bonding pairs. So that's going to put me in a tetrahedral group, but this one is tetrahedral and bent. That's going to be an sp3 hybrid, and then the bond angle for tetrahedral is 109.5. We talked about that being 104.5, but in this case, you won't know it for every molecule. So we're going to say less than 109.5. Then for this molecule, there are 3 bonds and 1 non-bonding pair. So that's still 3 plus 1 is 4. So that still puts us in a tetrahedral group, but it is trigonal pyramidal. And so that's still going to be sp3 and less than 109.5 degrees. Now, why did I draw both of these? It turns out that when I evaluate the polarity, this end of the molecule is negative or positive, and this end is negative. So this molecule is polar, as is this one. So it gives you 2 examples of a polar molecule, because you can get separation of the charge, but sometimes you have to pay attention to the shape to see that the polarities don't cancel. All right, sigma and pi bonds. We want to determine the number of sigma and pi bonds in cyanide Cn minus. And so we drew that structure before, so we'll use it and then just determine the number of sigma and pi bonds. So if you remember, this was the structure, and it does include 1 triple bond. So remember, I can't overlap more than 1 bond directly. So a triple bond represents 1 sigma bond and 2 pi bonds. And just to summarize that for every single bond you have, there is 1 sigma bond. The double bonds, there's going to be 1 sigma and 1 pi, because I have to share 1 either in the front and the back, or the top and the bottom. So the triple is going to be 1 sigma. You never really get above 1 sigma per bond, but it's going to be 2 pi's. So let's look at these. These all have more than 1 central atom. So we get C2H6, C2H4, and C2H2, and we want to get structures of those. In their case, the carbons will be the central atoms, and the hydrogens will be the substituents. Okay, let's draw the structures of these. First, we'll need to add up the valence electrons. Although with many organics, you can get by without, as long as you know what kind of molecule it is you're talking about. But we'll just go ahead and add them up. Carbon, there's 2 of those times 4, 8. Hydrogen, there's 6 of those times 1 for a total of 6. That gives us 14 electrons. Now the carbons will be our central atoms in an organic molecule. And then you must very well conceive that the hydrogens will be bonded around it to form our skeleton, equal number of hydrogens on each carbon. That makes common sense. Now if we evaluate our octet roll, 2, 4, 6, 8, 10, 12, 14. I just added all the electrons to the structure, so it had better add up right? Carbon has 4 bonds or 8 electrons in each case. Each hydrogen's happy, so that's a good structure. But you could imagine where you could draw that without going through the whole rigmarole. Now, we got C2H4, which is ethene. This first one's ethane. This is ethene or ethylene, which is commonly used in plastic. Still 2 of those times 4 is 8. Hydrogen, there's 4 of those times 1, which is 4. That's going to give us 12. I'm not going to quite have the amount to do what I did up here. So my skeleton is going to look more like this. So 2, 4, 6, 8, 10. That takes away 10. Leaves me with 2. Since the carbon is both still need 2, I need to double that bond to satisfy it. And that makes complete sense. Now, C2H2 is acetylene, which is commonly used in welding. And then the hydrogen excuse me, 2 of those times 1 is 2. That's going to put me at 10. But I really only have enough hydrogens to make a more or less linear molecule. That's going to take away 6 and it's going to leave me with 4. The hydrogens are happy, but I'm going to have to put triple that bond in the middle. And so that gives you an idea of how to work with more than one central atom.